All right, I think that's recording. So we were talking about general planar motion, right? I went into details about how to deal with this specific equation. This is a very, very, for the lack of a better term, powerful equation, very useful equation. If you get a hang of it and you know how to use it, there are so many problems that you can solve with this. And generally speaking, under general planar motion, when we talked about acceleration on Monday. Equation is simple, but you have to be very, very careful when you're implementing this equation. As you saw, I went over one example. You have to, as I said, you have to make 3 specific decisions. You have to decide where you want to put your local frame, right? The general, global frame is just some fixed frame, ij. You can always assume that in x direction is horizontal is x direction, vertical in y direction. We don't even bother most of the time figuring out where the general global frame is, because you're dealing with velocity, right? Velocity is the derivative of position or displacement, and as a result, we don't care that much about the absolute position because we're taking a derivative with respect to time. And what I'm trying to say is that we are very, very, we are almost not concerned about global frames in all cases. We just think about it as horizontal as x, vertical as y. Now, local frame is a different story. That's what it matters. We have to decide, again, 3 decisions, as I said, we have to make. We have to decide where to put it, right? Where you want to put this frame. What part of the system you want to attach it to, because it matters, it determines V relative and omega cross R terms, and also other terms, but specifically these 2. So where you want to put it, what component of the system you want to attach it to at the point that you put it, and which point you want to study using this frame. Now, these are 3 decisions you have to make. Now, rule of thumb says go for the part of the system you have the most information about. Right? Either put your frame there or put your frame somewhere else and study that point that you have the most information about. Right? Let it be part of the process, because you have the most information about that part. You have to use that information, right? Either put your frame there and study a different point, or put your frame somewhere else and study the point that you have the most information about. This is general rule of thumb, how to decide where to put it and what where to put it and what to study using that frame. I'll go over hopefully 2 examples today. I'll try to be a little faster so we can actually cover both examples. To clarify, I think this needs a couple, at least 2 more examples to clarify things. I want to start with this one. And the problem statement, if I can find it, I do have somewhere here. All right. So the problem statement is it, these are typically examples from your textbook. So not examples, I leave examples there for you to practice. These are basically problems from end of chapter most of the time. Okay, example, say we have this piston moving back and forth inside the cylinder. Now, the problem says at the instant, I can write it, instant shown at this specific moment, the piston's velocity is VC is equal to minus 14. I think it's represented by I, meaning along x-axis, meter per second. All right. Now, what he's asking you to find is what is the angular velocity of the crank AB. Crank AB. All right, so when it says 14 meter per second in I, means in X, this is your global frame. If you want to think about it, the way we represented that, we used upper case X and uppercase Y. It tells you that VC is 14 meter per second in X direction negative. So basically that means the piston is moving to the left with 14 meter per second velocity. Knowing that, we want to find out what is the angular velocity of link or more specifically crank AB. So decisions: where to put the local frame, what to attach it to, what point we should study. All right. Now, the point that we have the information about is point C. So I'm going to put my frame on point C because I have some information at point C. I want to take that into account. I want to have it in when I'm solving a problem. I want that to be part of the process. Right? So I put X, Y. That's where I put my local frame. And I'm going to attach it to the piston. Because piston is going back and forth, so it's pretty straightforward. I know its velocity. So attach to the piston. All right. So I decided where to put it, what part of this system attach it to, and now let's write the equation. Now the third part is what point I want to study. Well, there is really not that much. The only point I can study is B. I can't go for A, right? Because it's just A too far. There are multiple links there. You have to, if you go back to the general form, you see we have to study a point A using this local frame. Point B is pretty much the best point we can go for, or the only point we can go for if you put our frame on C. Now, what would the point of studying the velocity of point B? I want to give you some insights about why are we doing this. Remember, we're trying to find the angular velocity of crank AB, right? Now, point B is part of BC and part of AB. If we find the velocity of B, absolute velocity of B, then B is rotating around point A, right? This is the path it follows, which is a circular motion. So if I find the velocity of B, this velocity, is going to the left, so velocity is this way. If I find this velocity, and I know this radius here, I can find the angular velocity of AB, because we know VB is RAB omega AB. Right? If VB that direction, then omega is in this direction, omega AB, or omega angular velocity of this link. So if I can find VB, I know RAB, I can find the angular velocity of this link AB. Right? And that's why I'm studying point B is useful, because once I find this velocity, I can use it to find the angular velocity of this crank AB. That's just some steps forward to get a sense of why are we actually focused on that. We made three decisions: where to put the frame, what part attach it to, and we're going to study point B. So following the general equation, we say VB is equal to VC plus V relative plus omega cross R. All right. Let me erase this and clean up. Now let's look at these terms. Omega, we said, is the angular velocity of the local frame about its origin, right? That was omega. This is omega. Now in this case, our frame is going like this, going back and forth. So it's not rotating about its origin. So omega is 0. Right? In this case, this frame is just going back and forth. It's attached to a piston. So this is 0. Right? Now let's do a general analysis. For VB, let's start with VC, velocity of C. As I said, these are vectors, right? They have magnitude and direction. I've been emphasizing this. Right now, you see why. VC, we know its magnitude is 14 meters per second in negative direction along X. So we know its magnitude. I'll put it like this. No. If we can better, we know its magnitude. And we know its direction. It's along x-axis. Remember, VC is the absolute velocity of the origin of the local frame, or in this case, point C. And we know that it's 14 meters per second. We know the velocity, we know its direction. VB is the velocity of point B, absolute velocity of point B. I just told you that we know its direction, right? We know that it's perpendicular to this and it's in this direction because point B is part of link AB. So if this is R, this is perpendicular and this is the circular direction, right? Since point B is part of BC and part of AB, we know the direction when this piston goes to left, we know the direction or velocity of B. We know the direction of this velocity. So I know its direction, but we don't know its magnitude, right? If we knew its magnitude, we could find the angular velocity of link AB, but we can't. So we don't know its magnitude. Now, what is V relative? Let's figure out V relative. V relative, as I told you before, that to figure that out, freeze your local frame and whatever your local frame is attached to. So I'm going to freeze that red frame, and piston is attached to a piston, so piston is also frozen. Now, move the link BC. This is the frame, and let's say this is point B, this is point C. This is point C, sorry, attached to origin, this is point B. Forget about the rest of the system, just take into account the frame that you attach to, the local frame, and whatever is attached to it, and the point you're studying. Assume that these two are isolated from the rest of the system and can do whatever they want. Forget about BC being attached to AB. That's the general rule. You freeze the local frame, and whatever is attached to, isolate that part and the part that the point you're studying from the rest of the system. In this case, it's point B, which means the link BC, we can attach it from the rest of the system. So if you do that, I'm going to redraw it to make sure that you follow what I'm saying. This is X. I'm drawing the local frame. X, Y, this is point C. And this is point B we are studying. Right? And it's attached to C like this. Well, the gray is frozen. And now we see how B can move, the point we're studying, because we're looking for relative velocity and isolating everything, these from the system. So theoretically, forget about the constraint that it has when it's attached to a system. Theoretically, it can follow this circular path. Right? This is frozen. Where can this go? It can only rotate about this circle, in this circle. Now, if that's the case, it means this will be the velocity of that. If it's a circular motion, the velocity, the relative velocity would be this. This is V relative, VB with respect to point C. So make sure you follow this specific part. This is a tricky part, that what we attach to frame, when we attach the local frame to something, it determines the relative velocity of omega cross R. In this case, I froze the frame, red frame, attached it to piston, froze it, or you freeze it, the piston is frozen, whatever you're studying, whatever part that point is attached to, right? You just isolate that and the local frame from the rest of the system and see how that point can move if it's not attached to the rest of the system. Point B, right? It can move around point C in a circular path. That means that this is omega relative. So if this is rotating with some, let's say in this direction, if we're going in this direction, well, actually it's in the up. Well, let's just keep it this way. It can rotate in this direction, right, along this circular path. This would be your V relative. So we know the direction of V relative at this given moment. What we don't know is magnitude. We don't know what is the magnitude of that. Magnitude would be if we knew what is this omega, I'll call it omega BC. If we knew what this omega BC is, the magnitude would be V relative would be R BC omega BC. We don't know what omega BC is. We know RBC. RBC is the length. We can find it based on the geometry, but we don't know omega BC. So we don't know the magnitude of V relative. Now look at this equation that we have here. This is, you are allowed, let's put it this way, because this gives you a vector form. This is a vector form equation, right? You get components in X and Y direction, right? I and J. So you are allowed to have two unknowns. If you have two unknowns, it means this is gonna give you something useful and you can continue. If we had more than two unknowns, let's say we didn't know the magnitude of VC or the direction of VC, then we couldn't use it. It would have been useless. But now you have two unknowns. Let me continue these things, start making more sense, so explaining. So let's say VB, right? Let's go over these terms one by one. Right? VB, I draw it here. Right? I said this is VB because point B is part of BC and part of AB. So VB is whatever is the magnitude of VB, and we have to find its direction. I'm going to redraw it here to take a closer look at it. This is point A, this is point B, and this is VB. Right? I'm just saying VB is part of BC, but at the same time it's part of AB. So I want to write it this way. It's constrained by its motion around in a circular motion around point A. This we know, this is RAB, we can find. This is perpendicular to that. So that means this angle, well, we have to find the angle, right? The angle it creates with either this angle here or this angle, which they are the same. Well, not these two, sorry. This one and this one are the same. All right. And that angle is 45 degrees. Let me clean up here so we can actually look at it as, this is a right triangle there. This is, we're looking at this triangle here, and this is the angle. This angle is tan inverse opposite, which is 50 millimeters, divided by adjacent, which is 50. So theta becomes 45 degrees. Let me draw this line vertically. This is the angle, right? So this is theta, this is theta. So VB, whatever is magnitude, which we don't know, multiplied by, write it in XY components, right? We want the absolute velocity. So would be minus sine theta I plus, let's just put 45 now, you know, sine 45I plus cosine 45J. This is VB represented in magnitude and direction. As we said, we know its magnitude, we don't know its magnitude, or we know its direction. So we write it down. I'm going over the equation term by term. VC, I know its magnitude, I know its direction, right? It's given. So it's minus 14 I. Right? It's just given meter per second. If you want to draw it, this is VC. VC. V relative. V relative is, well, I draw it here. We know its magnitude is whatever R BC is multiplied by omega BC. It's going to give you a number. Its direction, well, you have to figure out the direction. Let's draw this. You have to find this angle. Either, I think we can find this angle, which is equal to this angle. Right? We can just use that, and then which is equal to this angle right here. So if I call this, I guess theta 1, because I use theta 1, theta 1. If I find theta 1, I can decompose this into XY components. Now, what is theta 1? Well, let's figure that out. Theta 1, I'll write it here. Theta 1 is tan inverse. Let's look at the geometry. Where can I draw it? Right, so this is theta 1, right? If this is the triangle here, this is theta 1. Theta 1 is tan inverse 50 opposite over adjacent 175, which gives you 15.945 degrees. All right. And we can also find RBC. RBC in the same triangle right here. And RBC, length of BC is a right triangle, is the square root of 50 squared plus 175 squared. That'll give you 182 millimeters. So this becomes, now you know theta 1, you have to decompose V relative in different direction. In X direction, it becomes minus sine theta 1I. And in Y direction becomes minus cosine theta 1J. Knowing theta, we know theta 1, we know RBC. And that's why we don't know the magnitude of V relative, because we don't know omega BC. These are all the terms. Now let's put all of them back into the equation, right? Plugging in, you will get VB. Let's see if I can find it. VB minus sine 45 degrees I plus cosine 45 degrees J. 45 degrees J is equal to minus 14 I plus, well, we know what R is. R is 182 millimeters. So I'm going to put 0.182 converted to meter. Omega BC. This is R. I'm plugging in R here. 0.82. We found it here. Omega BC minus sine. Let's see if I can move things a little lower here. There you go. Omega BC minus sine 15.94 degrees I minus cosine 50.94 degrees J. So this becomes your equation. As I said, this is a vector equation. So you get one equation basically in a scalar interpretation. If you think about it as just a simple equation, you get one equation in I direction or equation in j direction. Right? In I direction, all the components, better to say you have an equality, both sides, all the I components should be equal, all j components should be equal. So looking at I components on the left side, we have minus VB sine 45 degrees. On the right side, we have minus 14 and minus 0.8, 182 omega BC sine 15.94 degrees. And this is along I. Along J, you get minus, it's positive, so VB cosine 45 degrees, I can write it better, is equal to, from the right side, you get minus 182 omega BC cosine 15.94 degrees. So you have two equations, right? Two equations, two unknowns. Right? You don't know VB and you don't know omega BC. You can solve this. You have to keep this separated. There's nothing to do with that. This is for this. Right, two equations, two unknowns, then you can solve this and you can find, I think one way would be to move things to the other side, or maybe from even this side, you can just divide both sides. You can divide equation 1 by equation 2 and get tangent 45 degrees, which is 1. And then omega B will be canceled. You can find omega BC. Once you know omega BC, you can use that to find VB. I'll leave it to you. It's a simple two equations, two unknowns, right? Whichever you're comfortable solving it. But mathematically, you can find VB and omega BC. Right? If you do that, you can find omega BC is equal to and VB is equal to. This is the magnitude of VB. I've been just lazy. I didn't put the magnitude around. You get omega BC as minus 62.22 rad per second, and you get VB as 15.4 meter per second. There you go. This is your VB. This is omega BC. Now, omega BC turned out to be negative. It means the direction I took, like this light green I put there, omega BC in this direction, was not the correct assumption, which I figured it out, but I just let it happen. So we'll get a negative value, meaning that the actual direction of omega BC when this whole motion happens is actually counterclockwise, is clockwise. It's in the opposite direction. Okay, after all this, now we have VB. Knowing VB, we can find omega AB, right? That was the whole story at the beginning. I said we want to find VB. Once we know VB, we can find omega B, AB. If this is point B, and you know VB now, which is VB, it's magnitude. This is point A. This is R AB. So now we can say from there, then omega AB, or whatever that is, it's probably in this direction, omega AB, is equal to VB, the magnitude, over R AB. VB is 15.4 meter per second. And we found it. RAB, well, RAB is in this red triangle, right? RAB is the hypotenuse of this right triangle, which is a square, which means it's square root of 50 squared plus 50 squared. So that's the square root of 50 squared plus 50 squared. If you do that, you get 217.77. And the direction I took is the direction. VB is in that direction. So counterclockwise. That would be your final answer. Fun, huh? So a lot of places that things can go wrong. The equation is straightforward, but finding, and remember, I told you, I solved this in a scalar approach. Now, if you look at your textbook, they do a lot of cross product and do it in a vector base. Right? That's another approach. If we had time, I could just cover that approach too, but we'll just stick to a scalar approach. I find it more intuitive than vector operation. Vector operation might seem easier, but over the years I've taught this course, I realized that almost always, we go in the wrong direction. So that's the general story, right? You put the frame, study the point. You have to be cautious about each component. You go over each component one by one, write it in a vector form. You're going to end up having an equation that has both I and j components. And since it's an equality, I components from both sides should be equal, and j components from both sides should be equal. Right? You get two equations. From those two equations, you can find the unknowns you're looking for. All right. I'm going to start the second example. Question on this one before I move on. Yeah, this is the kind of thing that you have to practice a lot to get comfortable with it. And this is something you actually have to be comfortable before we start talking about acceleration. Because the acceleration story is that the velocity story added another layer, meaning that you have to actually now deal with acceleration terms. The equation becomes longer. The terms you have to figure out their directions and their magnitudes, they increase. So the reason we're spending time on velocity is because the underlying story is the same, but there are more steps and there are more things you have to take into account when it comes to acceleration. All right. Let me do another example. See, that one might clarify some other aspects of this process. Let me go back, stay here a little bit if you're taking notes. And give you some time if a question comes up. So you see, whatever we've learned in the first part of the semester is actually coming back. Motion around the circular path, R omega, finding the velocity, decomposing the vectors in XY components. Pretty much everything we learned is going to come back in one way or another when you look at the kinematics of a rigid body, which makes sense because we're extending kinematics of particles to kinematics of rigid bodies, right? Of course, it's built on whatever we know about particles and points. All right, let's look at something more challenging than that what we covered. Let's look at this one. Now, the problem statement says, right, this is a four-link mechanism. Right? Well, we only see three, but the ground also counts as well. So the problem statement says, bar where I'm writing it. Bar AB is, or better to say, rotates at 4 radian per second in the counterclockwise, this direction, counterclockwise direction. Find the velocity of point C. All right, this is point C. We know AB is rotating counterclockwise, which basically means it's going in this direction. Right? This is the direction it's rotating. All right, so where to put the frame, what point to study? Oh, I'm going to put the frame on point B, because point B is part of link AB, and I know the angular velocity of link AB. And remember, I want to study point C, so I want to be as close as possible to point C, but at the same time, use the information I have in the problem statement, which is the angular velocity of AB. So I'll put the frame on point B right here and attach it to the bar. So this angular velocity of the bar is useful. All right. I'll put it this way. Let me see if I can figure out. Let's put it this way, straight. X, Y, and this is the origin. I'm sorry. So this is my local frame, and it's attached to link AB. All right. Now let's try to study point C, see what happens. I put it on point B, attached it to link AB, and I'm going to study point C, right? Because I want the velocity of point C. So that means VC is equal to VB plus V relative plus omega cross R. For multiple reasons I brought this example. We'll see. First, omega cross R term. Let's look at that. You have this frame attached to link AB, right? So when link AB rotates, this is what happens to your frame, right? Your frame goes with this link like this. Okay? Remember, omega is the angular velocity of local frame when it rotates about its origin. In this motion, this is not happening, right? You don't see local frame rotating about its origin. It's attached to this link. So when this link moves, it moves like this. So the omega of this link is not the omega that we care in this omega cross R. That omega is the omega of the frame rotating about its origin. But this frame is not rotating about its origin. This frame is attached to link B, so it goes like this. So this is 0. Very careful, be very careful about this omega. That's a good question. You can always do that, actually. There are some cases now, we will go when we move into acceleration. I'll bring up an example or two. There are some cases that both terms exist, though. Most cases, either V relative exists or omega cross R. Right? So if you attach it to, in this examples like the link, you get rid of omega cross R, so your life is much easier. You know? If you attach it to the, let's put it this way, if I attached it to the plate in this case, for example, if I attached it to the plate, yellow plate, then we would have had omega cross r, because this frame, it's moving with this link, but at the same time it can rotate, right? Remember, this system is moving in this way. This is rotating, this is also rotating, right? This whole thing is moving. I don't want to make it confusing, but if you attach this frame to the yellow plate, you would have had omega cross r. So you're right, you just can attach it to the link and get rid of omega cross r. But there are cases that the point we're studying is not exactly, so if the point we're studying, I have to bring those examples, but for most cases, try to do that. Yes, it's a good idea. So you just deal with V relative. But there are cases that both exist. So I'll probably put it in some of the sample problems I'll share with you. All right, so omega cross r is 0. Now we have V, we have other terms. Let's take a look. We don't know about VC, anything about VC. We don't know its magnitude, we don't know its direction. VC is this point that is on the plate. So depending on how these other links move, it can move in any direction in the space. It's not attached to any link, attached to the base or grounds that we can say it's following a circular direction. So we don't know its magnitude and we don't know its direction. We don't know anything about point C velocity. VB we know, right? VB is part of also link AB. So VB is similar to the previous example. VB is this, right? If we have omega in this direction, this would be the direction of VB. So we know its magnitude and its direction. Good. V relative is the velocity of point C with respect to point B. The frame is attached, V relative. How do we determine that? Freeze the frame and whatever the frame is attached to on the link. Right? So it's both of them are frozen. Now move the part that the point you're studying is part of, move that part, assuming that nothing else exists in the system. So in that case, this C rotates around this origin or follows this circular path, right? If you freeze the frame and the link attached to it, whatever it is frozen, you can only move the plate in this case, right? The point, this part that the point is part of. If you move that, you know that this would be your V relative. You'll get, if let's say, assuming that this is the direction of the rotation of this plate, if I can get this to work, this would be your V relative. So you know its direction. You don't know its magnitude, but you know its direction. See what happened? We have a problem of 3 question marks there. We said this equation can only afford having 2 unknowns, magnitude and direction, because it gives us one equation in I direction and one equation in J direction, or one equation in X direction, one equation in Y direction. Always have to change this because the notation textbook is lowercase x1. This is the global frame. So that equation is not useful. It's not going to give us enough equations for the number of unknowns. What do? We are going to change your the way we look at this. Where is this? We are going to look at, instead of, no, the local frame is attached. The frame is attached to link AB. So when I wanted to find the V relative, I said, well, I'm looking at point C, right? If it's attached to link AB, I freeze the frame and the link AB. Now, plate can move because I start moving the part that the point I'm studying is part of. So I start moving the plate as if it's not attached to anything else in the system. And I say, well, that gives me V relative. VC with within local frame, and that's how I got VC, or V relative, not VC. VC is absolute velocity of point C. V relative, we see in local frame. Right? Frame is attached to link AB. Now, what do? I change the point I'm studying. Instead of point C, although I want the velocity of point C, but I can't solve for C now. If I look at point D here, if I look at point D, the story changes. If I instead if I write VD, velocity of point D, is equal to velocity of point B, same frame, I'm studying a different point on this plate. VB plus V relative plus omega cross R. Now, I still don't know, well, I know VB, V relative, velocity of D in local frame. So this is following this path. Same story, it's following this path. Frame is attached to the link. So D is, if you start moving the plate, you'll see D is following a circular path about the origin of the local frame. So you know its direction. Right? Assuming that the plate is rotating in this direction at this given moment, this would be the velocity of D, Vt, given this distance from origin to point D. All right. So we don't know the magnitude of V relative. This is not Vd, this is V relative. V relative. We know the magnitude of V relative. We don't know the magnitude, what we know is direction. Omega cross R is still 0. Let's look at VD. Now, what changed? I moved from C to D. The big change that is going to help me is that now I know the direction of the velocity for point D. Why? Because point D is also part of link BD, link DE. Right? This point is part of this link. That means I know its direction. Right? It can only rotate about this point. It doesn't matter what is the motion of the whole system. By the end of the day, the velocity of this, depending on which direction, we are going to assume that link DE is rotating. We have to make an assumption about that. We can say, if I make an assumption that it rotates this way, I can say I know the velocity of VD, its direction. This is VD. I couldn't make the same assumption about C because C was floating, like it wasn't connected to anything. But D is part of link D, which means it's going in a circular path about point E, which means I know its direction. I don't know its magnitude, but I know its direction. Now this is good. I have two unknowns. VD, I don't know its magnitude. V relative also, I don't know its magnitude. But other parameters, I know. All right. That's the important part. The rest is just doing what we did before, like finding the angles, figuring out how to decompose vectors. Right? You can say VD is equal to magnitude of VD, whatever it is, which actually you can write it as, let's just keep it that way. So, magnitude of VD times, this is VD. Because these, and let's say this is omega, let's say it's rotating this way, so it's perpendicular to that. And we need to find this angle to be able to decompose this. We need to find this angle. I'm going to call this theta 1. That angle is equal to this angle here. Theta 1. And theta 1 is tan inverse. Whatever is in the opposite is 300 over whatever is adjacent, which is 500 in that right triangle. That will give you tan inverse of 0.6. Let me double check. I think 30 something. 30.696 at least. Degrees. Theta 1. Once you know theta 1, you can decompose VD, right? This is VD. VD becomes minus cosine theta 1 I minus sine theta 1 J. So look at VB. I'm just going over terms one by one. VB, we figured out this direction, right? This is VB right here. So VB is whatever VB is, R AB omega AB, right? Whatever the magnitude of that, multiplied by, we need to find this angle. Let's call this, or maybe the other angles might be easier. You can find this angle here, theta 2, and this angle is, I really draw it in a bad way. I think this angle is the same as this angle, theta 2. Theta 2 would be tan inverse. Whatever is the opposite is 600 divided by adjacent 300. Right, theta 2 gives you 63.435 degrees. So knowing that, and you can also find what else you need. RAB, you need that. So RAB is the square root of 300 squared plus 600 squared. Right. That'll give you 670. I don't remember what the value. If someone calculates this, I don't have it in my notes. I'll leave it. There's some other digit there. 670 something. Oh, 67, yeah. 67 point, yeah. I can't read my notes. That is true. 67.08. Thank you. Great. So you know RAB, so it's 67.08 millimeters, or better write it in meter. Right, so let's just put it divided by that, 6, 7. Probably I'll just keep it that. Then in x direction, you have minus sine theta 2 I, right? Remember theta 1 and theta 2, you know. Plus, in y direction, cosine theta 2 j. 670. All right, I'm glad someone fixed that. It should have been 6 times. Craig, I'm looking at you. 670 point, I think it's too small. 8. Thank you, Caitlin. You should have known, she should not trust Craig. All right, so RAB now we know. We keep it that way. We looked at VD, VB, and V relative is equal to, like V relative times, what we don't know is magnitude, the direction of that. Let me draw it here because that might be hard to see. If this is X and this is Y, local frames, this is X, this is Y, this is V relative. So point D here, that'll give you V relative. So I draw it, let's say the, assume the angular velocity to be in this direction. You always make that assumption. That'll be omega, I'll call it omega plate, omega, whatever the omega of that plate is, and put the velocity here. This would be V relative. So what I care about is I want to find what is this angle. I have to find the component. So I need this angle, or which is the same as this angle, called theta. Maybe we should use a different color. It's called theta 3. And theta 3 would be what? Tan inverse. Looking at the geometry there, we have this, this, and this. So becomes tan inverse 600 minus 500. That length is 100. divided by whatever is this length, which is 600 plus 200, 800. So theta 3 becomes 7, I do have that one, 7.125 degrees. So this becomes V relative multiplied by minus sine theta 3I and minus cosine theta 3J. These are going to be components in this equation. So then you do what you did before. I'm going to move this here because that is taking space for no reason. And we plug everything in, you'll get in I direction, and I'll just write those. In I direction, you will get minus VD cosine theta 1 is equal to minus 2.683 sine theta 2 minus V relative sine theta 3. These are components in I direction. In J direction, you'll get minus VD sine theta 1 is equal to 2.683 cosine theta 2 minus V relative cosine theta 3. All right. Unknowns are VD, you know the angles, and V relative. Right? We don't know VD, we don't know V relative. Again, two equations, two unknowns. We can find the unknown values. VD becomes 3.2144 and V relative is 2.8756 meter per second. I'll continue this next class. There is one more step we have to take because now we know the velocity of D and V relative. Right? But then what? What is we were looking for velocity of point C, right? That's not what we have. We still have to go one more step. Now, the logic is once you know VD and you know V relative, once you know V relative is omega plate times the distance, right? That point D had from the origin. So dividing this V relative by that distance, you can find the omega of the plate. Once you know the omega of the plate, it means you know you can find VC. So you can go back to the first equation, this equation right there, because now you know the direction of VC. Now you know, V relative. Right? So you plug in V relative to the previous equation and you can just solve it. If you can just actually go directly. We'll talk about it in the next class. I'll just let's just jump into the quiz, then we'll